So this is my final quantitative question for my Physics 122 final. So we have our question. A particle with the charge q is located at the origin and a particle 5q is on the positive x-axis. That is a distance d from the origin. The particles are not free to move, so they are bounded to the x-axis. In terms of q and d, at what coordinates should the third particle be placed so that it experiences no net electrostatic force? Assume it is on the positive x-axis for our third particle. So we have two major concepts primarily that this deals with here. We have electrostatic forces, specifically Coulomb's law, and the second one would be Newton's law of motion back in mechanics, specifically Newton's third law. This is important to understand how Coulomb's law applies here. So some key ideas we should apply here is that Coulomb's law. From Coulomb's law, we have charged particles have a force. They apply a force. Specifically, since we're dealing with positive charged particles, they're going to apply an outward force. Similar, and as well as similar charges like to repel. So positive q and another positive q will repel. We also have Newton's third law, which is the total force is equal to the sum of forces. We'll get more in depth with that later. So we have a picture here to show what this all looks like. We have positive q at the origin at 0. We have our second particle 5q somewhere on the x-axis, d distance away from the origin. Then we have our third particle, positive q, which is r distance away from the origin. So the final quantity we want is this r distance away from the origin in terms of q and d. This is without units, of course, because we are not given any, so we can't know if it's meters, picometers, or anything else. So we're just going to leave it in terms of q and d. So formulas we need to know for this are electrostatic force is equal to Coulomb's constant multiplied by charge being q, over the distance away squared. The distance from the point you're measuring squared. So, and Newton's third law over here, sum of forces in the x direction specifically is going to be F1 x minus F2x. And we can equate that to Coulomb's law, saying that electrostatic force, or sum of electrostatic force in the x direction, is going to be E1 in the electrostatic force in the x direction minus the electrostatic force in the x direction, and that should equal 0. Why it's not plus? Because usually we have plus with Newton's third law, F1x plus F2x. We have minus because, as I said before, charges like to repel. So this charge 1 is going to be pushing charge 3 this way, whereas particle 2 is going to be pushing the third particle this way. So they're going to be pushing against each other. So we've determined this as the positive x-axis. Since charge 1 is going to be pushing this charge in the positive x-axis, and our second particle is going to be pushing particle 3 in the negative x-axis, I've determined that we can just subtract the force that the third particle is applying on particle 2. So we get that the sum of forces here should still be 0, but instead we have minus electrostatic force of particle 2 in the x direction. So now that we have everything we need, we have our solution over here that we find the electrostatic force of particle 1, which is kq over r squared. We can keep it as r because that is the variable we're using to solve for. Then electrostatic force 2 is going to be k5q d minus r squared. Why it's not just d is because we want the distance from particle 3 to particle 2, which is going to not be d, it's going to be d minus r. Of course, squared, because we still want to square the distance where the distance that we are away from whatever we're measuring. So we can put that in our Newton's third law derivation, that we have the sum of electrostatic forces in the x direction is kq over r squared minus k5q over d minus r squared equals 0. Bringing this to the other side, we have kq over r squared equals k5q divided by d minus r squared. We can cancel out the k's. We could cancel out the q's if we wanted to, but it wanted it in terms of q, so we're going to keep it there for now. So we can bring our d minus r squared to the other side by multiplying it. Then we have d minus r squared over r squared equals root 5q. Oh, sorry, equals just 5q. But then we square each side in order to get rid of these squares here. And we're left with root q times d minus r over r equals root 5q. Then from there we can multiply by r, add r. We have root qd is going to equal root 5 times r plus r. We can factor out our r and we're just left with, on the right side, root 5q plus 1 equals root qd. We have our r on the outside here, so now we can just divide by root 5q plus 1. And then we are left with r equals root qd over 5 root 5 times q plus 1. Of course, we could cancel out these root q's here, but we want it in terms of q, so we're going to keep it that way. Because q could be anything, it could be 1, 2, 3, 4, or 5 over, so we're just going to keep it there. So that means the third particle should be root q times d over root 5 times q plus 1 units, because we don't really have any units to apply on the positive x-axis from there to be zero, to have a zero net electrostatic force on it. So that's what r is going to be here. It's going to be root q times d over root 5q plus 1, distance away. Thank you.